Hello dear students, this is B. Veeramat. Today I am going to discuss one of the very important topic in the current electricity, that is the sixth part of current electricity. So in the current electricity we need to discuss the concepts of combination of resistors. Then combination of resistors, they can connected in two types. One is series connection of resistor, another one is parallel connection of resistors. The first one is the combination of resistors in series. See, the resistors are said to be connected in a series when they are connected end to end. If the resistors which are connected end to end, see, so one end of the resistor is connected to next end of the another next resistor, then the another end of the this resistor is connected to one end of the another resistor, like this. If such type of connection, we can call it as series connection. That is, the resistors are said to be connected in series when they are connected in end to end connection, such that the here in the given circuit that shows, first there are two important things is here we need to note, in which first one is the same current flowing through each of the resistors. See, this is the current which is flowing to each resistor, that is a same current. The same current flows through each of the resistor, first thing. Then second thing is the total potential difference across the combination is equal to, see, the total potential difference across the combination, that is equal to the sum of potential difference across the each resistor. The total potential difference is equal to sum of each resistor. That is the second thing we need to keep it in mind. So now we want to derive this the combination of resistance if they are connected in series. See, so let us consider three resistors. See, let us consider three resistors R1, R2 and R3 connected in series as shown in the figure. Let V be the potential difference across the combination. See, there is a total potential difference is there. So that is a V be the total potential difference across the combination. Then I is the current through the resistor. See, this is the current, so which is passing through the resistor, that is same through each resistor here. And so there are some, see, there are some potential difference are given here, that is V1, V2, V3, like this. If V1, V2, V3 are the potential difference across R1, R2, R3 respectively, then V is equal to, total V is equal to V1 plus V2 plus V3, that gives a total potential difference across the combination. See, so according to this derivation, here 1 minute. See, so as per the consideration, consider three resistors R1, R2, R3 connected in series. Let V be the total potential difference across the combination and I be the current through the resistor. Then if V1, V2, V3 are the potential difference across R1, R2, R3 respectively, then total potential difference is equal to V equal to V1 plus V2 plus V3. So from Ohm's law, we know that V is equal to IR. Hence, V1 is equal to I into R1, because so the I does not changes to each resistor. It is the same value. The I value is same. Hence, we could, if we apply the Ohm's law through this, then formula is V1 is equal to I into R1. Then if we apply the Ohm's law across this resistor, that is V2 is equal to I into R2. If Ohm's law is applied to third resistor, then V3 is equal to I into R3. That is given here. So if Ohm's law is applied, then V1 is equal to IR1, V2 is equal to IR2, then V3 is equal to IR3. Then total V is equal to, we know that here that is given here, V is equal to V1 plus V2 plus V3. Hence V is equal to V1 means we have IR1 value, hence it is IR1, plus V2 value is IR2 here, plus V3 value is IR3 is here, hence it is V is equal to IR1 plus IR2 plus IR3. That is equal to, here I is a common term, then keep it outside, then remaining terms are R1 plus R2 plus R3. If the combination of resistors is replaced by an equivalent resistance, that is Rs, in place of combination of resistor, if we replace one more resistor, see, if we replace all these three resistors, so then that's equal to, there is a one resistor, see, that is equal to, that is V is equal to I into R, that is shown here. See, V is equal to IR, which is represented in the diagram. This is the equivalent resistance. If we replace these three resistors, then that is equal to, so one equivalent resistor of its equivalent resistance. So that's the potential difference is equal to, V is equal to I into Rs. So from Ohm's law, V is equal to I into Rs. Hence, then according to this above equation, then V is equal to I R1 plus R2 plus R3, that is we wrote here, V is equal to I R1 R plus R2 plus R3, then from this V is equal to I into Rs. Then in place of V, I will replace this IRS, hence this becomes here, that is IRS is equal to I into R1 plus R2 plus R3. Then I and I get cancelled here, then remaining term Rs is equal to R1 plus R2 plus R3. This is equation number 1, and this is an expression for the combination of resistance, that is equal to, the combination of resistance is equal to the sum of resistance of the each resistor, that is R1 plus R2 plus R3. See, the number of resistors are connected in series, then equivalent resistance is equal to sum of individual resistance. Then the resistance are connected in series to, actually this is the one method, so we are connecting these resistors in series to get higher value. Hence the resistances are connected in series to get the higher effective value from the lower resistances. So this is the one method to increase its effective resistance. The next one is the combination of resistors in parallel. So the next concept is combination of resistors in parallel. Here the resistors are connected to be parallel when they are connected between two common points. See, there are three resistors. Let us consider three resistors R1, R2, R3, which are connected to only two common points. See, this is A, this point is considered as a and this side is considered as a B. So the A and B are the two points. All three resistors are connected to these two common points only. See, the resistors are, the resistor R1 which is connected to A and B, then second resistor R2 is also connected to AB, then third resistor R3 is also connected to A and B. So this is the definition. So according to this definition, the resistors are said to be connected in parallel when they are connected between two common points. These are the A and B are the common points. If the many resistors are connected to only two common points, and that type of connection we can call it as parallel connection. See, in the parallel, when the resistors are connected in parallel, so we need to observe two things, in which first one is the potential difference across each resistor is same. See here, for all three resistors, the potential difference across All three resistor is same, that is V. For first resistor its potential difference is V. For second resistor its potential difference is V. For third its value is V. This is the first thing. The second thing, the main current is equal to sum of currents through the each resistor. See, the total current is equal to, or main current is equal to the sum of current through each resistor. See, when this current I, which is divided into I1, I2 and I3, I1 is a current passing through the R1, I2 be the current passing through R2 and I3 be the current passing through R3. Then that after this all three currents meet at a single point, and again so the main current is becomes I. This is the second thing to be note. See, according to consideration, let us consider three resistors R1, R2, R3 which are connected to two common points. So this connection shown in the figure, that is as a parallel connection. Let V be the potential difference across the combination, and I be the main current. See, I be the main current. I1, I2, I3, I1, I2, I3 are the currents through the resistor R1, R2, R3 respectively. Then I is equal to I1 plus I2 plus I3. See, so that is this is the main consideration and given explanation like this. So as like a given figure, then the total current I is divided into I1, I2, I3, the currents passing through the resistor R1, R2, R3. After this current I1, I2, I3 becomes I. Then that's why I is equal to I1 plus I2 plus I3. From Ohm's law, so we know that V is equal to IR, then I is equal to V divided by I. Hence, from Ohm's law, it becomes V is equal to IR, then I is equal to V by R. For the first resistor, its value is equal to I1 is equal to V divided by R1. This is I1 is equal to V by R1. Then for second resistance, then I2 is equal to V by R2. For third, its value is I3 is equal to V divided by R3. Then from this equation, I is equal to I1 means V by R1, that is here, plus I2 means V by R2, that is here, I3 means V by R3, that is here. Then in this equation, V is a common term, keep it outside. Then remaining terms are 1 by R1 plus 1 by R2 plus 1 by R3, that is here. If the combination of resistor is replaced by equivalent resistance Rs, see, this is the diagram. See, this is the diagram. Here R1, R2, R3, and the combination of resistors which is replaced by a one resist, that is equivalent resistance Rs. Then the effect, the both effects are same here, the same effect as that of the combination. This equivalent resistance having the same effect that of the combination. Hence, according to Ohm's law, it's V is equal to RP. This is, we can take it as RP. V is equal to I into RP. Then I is equal to V divided by RP. That is shown here. I is equal to V divided by RP. Then, so that is equal to V divided by RP, because see here the equivalent, in the equivalent circuit I is equal to V by RP, then V by RP is equal to, that is V, if we take V keep it outside, then 1 by R1 plus 1 by R2 plus 1 by R3, or V and V get cancelled. So after this we can take it as 1 by RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is an expression for the combination of resistance in parallel, if we connected in parallel. So when the number of resistors are connected in parallel, then reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. The resistors are connected in parallel to get the lower effective value of the resistance from higher value of resistance. See, this is the combination of resistors if we connected in parallel. That is because of the reason. So if we want the value of a higher resistance from the combination of lower resistance. See, the next one is a cell. See, the cell is nothing but it is a simple device used to maintain the steady current in the electrical circuit. So in the given electrical circuit, a device which is used to maintain the steady current, that is what we can call it as a cell. See, the cell which consists of two electrodes, the cell which consists of two electrodes, one is a positive electrode, another one is negative electrode. One is a positive electrode, another one is negative electrode. These two electrodes are immersed inside the electrolytic solution. See here. So this is a one beaker or a container here in which there is a electrolytic solution is there. So then these two electrodes are immersed into the electrolytic solution. When the immersed in the electrolytic solution, the electrodes are exchanges the charges. These, because of these electrodes which are immersed in the electrolytic solution, then these electrodes which exchanges the charges. This electrode loses the electron and this electrode gains the electron. Electron are nothing but charges. That's why these two electrodes are exchanges the charges with electrolyte. As a result, the positive electrode acquires a positive potential, and this electrode acquires the positive potential, and the another electrode which acquires the negative potential. See, we are represented as a minus sign. Then, so that is, this is, you can take it as a V plus, and this is you can consider as a V minus. See, similarly, actually that as like this is a negative electrode, its potential is minus V relative to the electrolytic solution adjacent to it. Then when there is no current drawn from the cell, the electrolyte has the same potential throughout the potential difference between the two electrodes. One is we can consider as an anode, another one is considered as an cathode. Hence, so the potential difference E between these two electrodes, that is V plus of V minus. Here the potential difference between these two electrodes when there is no current drawn, that potential difference between these two we can call it as EMF, that is an electromotive force. What is the definition of an electromotive force? See, the electromotive force is the potential difference between the positive and negative electrodes of the cell when there is no current drawn from the cell. This is what we can call it as EMF. Now consider a resistance, or if we connected in place of this, if we connected somewhat resistance, then the steady current I is flowing through the circuit, that is flowing through the R in the direction from this to this. The direction is represented here by the arrow mark like this. Then while this current is flowing from positive electrode to negative electrode, the same current flowing through one electrode to another electrode, the electrolyte through which the current flow has a resistance. So if the current is flowing through this electrolyte and there should be some resistance, that resistance, or we can call it as internal resistance. See, the internal resistance of a cell, the definition is like this: the opposition offered by electrolytic cell. See, because due to the when a current flowing through this electrolyte, there should be some opposition or a resistance. The opposition offered by the electrolyte of a cell to a flow of current or electric current through it, it is called as internal resistance of cell. The factors affecting the internal resistance of a cell. One is, a larger the separation between the two electrodes of a cell, more is the length of the electrolyte through which current has to flow, and the consequently higher value of internal resistance. See here, if the distance between the two electrode is large or separation is larger, then the current has to flow larger distance, and there should definitely there should be a more opposition or resistance. The second one is, greater the conductivity of the electrolyte, lesser is the internal resistance. If the conductivity is more, then opposition is less. The internal resistance depends on the nature of the electrolyte. The third one is, the internal resistance of a cell is inversely proportional to common area of the electrodes dipped in the electrolytes. Here the electrolytes are dipped into the electrolytic solution, then the internal resistance is inversely proportional to area. Then internal resistance of a cell depends on the nature of the electrodes. Thank you.